Excellent. All right, thanks for that introduction. Good morning. I am Melissa Sampson. I'm with United Launch Alliance. I'm here to tell you a little bit about our company, but more importantly, what are we doing with space? Where are we going next? What are some of the innovations that are coming up very shortly for us as a community, specifically really looking at the Cislunar economy and the Cislunar arena. So the first thing I want to start with is a little bit about who we are. We are a rocket company, so we design, build, and launch large rockets. Right now we have 128 launches in a row with 100% mission success. We are extremely proud of this record. And one of the reminders for us is that it's always one launch at a time. So you'll see that on this slide, there's a little gray box without a picture. This is always our next launch. Our team is incredibly capable, but we are always focused on the next launch to make sure that that mission is successful for our customers. So while I love this slide, I also love that we have one box that is always empty on this slide, looking to the future and looking to our next customer. Our product lines today are Atlas V and Delta IV. We launch out of Cape Canaveral and Vandenberg Air Force Base in California and Florida, just as many of our friends here all do. And I do really want to say how excited I am to be here today. There's so many of our partners and friends in this audience. So it's a really special collaboration and really excited to be part of it this year. So who do we serve? Who do we launch for? So we are a larger rocket. Our fairing diameters are around 4 meters or 5 meters, depending on what the customer needs. We cover national security space, so GPS. We've launched every GPS satellite between United Launch Alliance and our heritage companies. We also work with the intelligence community, such as the NRO organization. Also, commercial space. So Earth imagery, commercial communications. The other area where we do a lot of work is civil space. So when we're talking about space science, we do a lot of work with NASA. We've launched every Mars rover that's currently there. We've launched missions to every single planet in our solar system, among some others. I will include Pluto in that list, and we can debate whether it's actually a planet or not. And then we have also launched satellites such as GOES and CloudSat and some of the other Earth observation satellites. So it covers everything from our life on Earth here today, our security, our well-being as a species, and what are we going to do next? Where do we want to go next? And how do we continue the science that comes along with this great arena of space that we have open to us? And then, of course, human launch is coming up. We are partnered with Boeing to launch U.S. astronauts to the International Space Station. So talking about our roadmap, what are we doing? So it's great that we have 128 missions. It's a very reliable process. But one of the things that we're doing is creating the next generation rocket, both the booster and the second stage. So as we walk down the chart, you'll see that the Atlas V is one of our workhorse class rockets. It has quite a few launches under its belt. It does have a Russian engine on it, though. So we are phasing that out to move to an American engine, which we're very excited about. So in a few years from now, it will be phased out as a product line. For the Delta IV, we have two classes of the Delta IV rocket, a medium and a heavy. The Delta IV medium has already been retired, so that is no longer a product that we're selling. We do sell the Delta IV heavy, and this is primarily for very, very large satellites, usually in the intelligence community. The Delta IV does have a projected retirement date, but we are absolutely committed to making sure that our customers have the products that they need and that they can get their satellites wherever they need to go. Most interestingly is the bottom line. This is really what I'm here to talk about today. So Vulcan is our next generation rocket. And it's either Vulcan Centaur or Vulcan Aces. Centaur and Aces are the second stages. So you'll see in the first box, we start with a Vulcan Centaur. Centaur is actually the second stage on the Atlas V today. It's one of the highest performing second stages in the world. And so we are taking that Centaur second stage, moving it from Atlas onto Vulcan. So we're looking initially in 2020 at about a 25-ton payload class. We will then upgrade Centaur again in 2023 timeframe. This will increase the performance up to 35 metric tons. We do have options for solid boosters. We can put anywhere between 2 to 6 solid boosters on the rocket. The rest of the rocket is liquid fueled, so the only solids on it are the smaller boosters on the first stage. One of the interesting items with Vulcan Centaur in the 2023 timeframe is that it will replace the performance of a Delta Heavy. So we will move from a 3-core or 3-booster rocket with the Delta IV Heavy into a single-core, single-booster rocket with the Vulcan Centaur. So we will have actually more performance than a Heavy with much lower cost. Then we move to Vulcan ACES. ACES is an upgrade to the Centaur, again, looking in the 2023 timeframe. ACES is going to be very unique because of an integrated subsystem. I'll talk a little bit more about that later on in the presentation. ACES continues to increase performance, and most importantly, ACES has an extremely long mission duration lifetime. Right now, most second stages are limited to about 6 to 8 hours on orbit, and that's across all of the launch vehicle providers that are flying today. ACES can go anywhere from days to weeks to months on orbit. So what we've done is eliminated some of the bottlenecks, and I'll talk the details later in the presentation. So the Vulcan ACES is really what is going to enable cislunar exploration, missions, and science. A couple other items that are also on our roadmap, smart reuse. This is capturing the engines from our booster stage to reuse the engines. Our vision of reusability is that with our first stage, most of our cost is in the engines. So for us, what we really want to do is recover the engines and reuse them. For us, we're not as concerned about the structure for the first stage. Distributed lift and propellant transfer. Another feature of the ACES second stage is that it is completely refuelable. In space, preferably. So this means as long as you have a gas station, you can keep running your second stage. So this changes from a model of having to come back to Earth to either refuel or refurbish to leaving something in space that can actively be utilized. As it was mentioned in the speaker before me, you were talking about the rocket equation. So if I don't have to bring my second stage back into Earth's gravity well and pay the launch costs and pay the propellant costs to get something back out of Earth's gravity well, there's huge savings in that reusability model to leave something in space. And then finally, these capabilities with the Vulcan ACES and ACES specifically bring us to cislunar space transport and the refueling concept. Here's a quick schematic of the Vulcan ACES. So we are still doing the engine trade for the first stage. It is a liquid first stage. We run on liquid oxygen and RP1, which is a refined kerosene, cleverly named RP1 for Rocket Propellant 1. Very technical. Our second stage for both Centaur and ACES will eventually be a 5.4 meter diameter. They are both liquid hydrogen and liquid oxygen on that upper stage. So talking about the cislunar ionosphere, why do we want to go there? What can we do there? What are some of the opportunities for commercialization to benefit humanity and to really expand what we're doing beyond Earth's surface and beyond LEO? So one of the things that's recently been discovered is that there's water on the moon. There's water in a whole lot of places within our solar system and relatively close to Earth. The moon's really in our backyard, and there are huge amounts of water there. Once you can access water, not only do you have water itself, but you can create oxygen for people or fuel. You can create hydrogen, so you can create liquid hydrogen, liquid oxygen, which is what our second stage happens to run on. So you can use it for both the rockets and the people in a variety of manners. It also creates power. You can use liquid hydrogen either for rocket fuel or to generate other types of power. Another opportunity within the Cislunar economy, is manufacturing in space. There are companies today that are looking to manufacture materials in space because it gives you a better purity of product. ZBLAN, which is a fiber communications material, is one of those. Pharma is another area. And I can only imagine all of the arenas of science that as we are able to spend more time and resources looking at microgravity, experimenting, and actually building things in microgravity, huge opportunities. Also, manufacturing in space eliminates the constraints of a payload fairing. So as was mentioned, right now, payload fairings do limit size, and so there's a lot of ways that people fold their satellites or have to make adjustments in their design to fit it inside a fairing. If you're assembling in space, that relieves that constraint. Okay, so let's come back to ACES. Why is it different and why is it revolutionary? So one of the things that we'll have is next generation avionics. We are continuing to upgrade our avionics, but particularly for deep space navigation and extended space navigation, a very much enhanced avionics suite will be necessary. Cryofluid management. Because liquid hydrogen and liquid oxygen are both cryogenic fuels, we have to make sure that they are not boiling off and disappearing when we are in space for weeks or months. When you're looking at an 8-hour time frame, boil off is not as much of a concern. It's pretty minimal compared to the amount of propellant you have. But for the longer durations, making sure that your fuel does not disappear is going to be very critical. So there's some great companies working on this technology now, and we are very, very excited to put some of this on our second stage. And then most interestingly is an integrated subsystem for both power and propulsion. So this is not only your thrust for the stage, but also electrical power, both to the stage and electrical power to payloads. So how does this work? So this integrated subsystem, it runs on liquid oxygen and liquid hydrogen. So it's running on the exact same fuels as the rest of the stage. So we now have a stage that is completely reliant on only two propellants, liquid hydrogen, liquid oxygen. What this allows us to do is, number one, we can take the batteries off of our stage. Batteries are very life-limiting for second stages, and they work great for a few hours, but once they run out, there's no way to recharge them in space. So by generating electricity that powers the stage, and I'll mention it again, but the opportunity to provide payload power and payload electricity is unique. Right now, payloads are reliant on their own batteries or other sources of power. So this provides something where the payload doesn't have to take up mass necessarily to provide some of the electricity that it needs. Second, we are eliminating hydrazine. Hydrazine is used for small thrusters for attitude and reaction control. The middle picture is a picture of the H2O2 thrusters. It's a few pounds of thrust. They're very small, just for minor adjustments. But again, hydrazine is a life-limiting storable propellant that once you're out of hydrazine, you can no longer run your ACS thrusters on the stages today. And third, it does pressurize the tanks. So right now, as we use propellant, we use helium to make sure that our tanks are staying at the right pressure. Once you run out of helium, you can't pressurize your tanks, which means you can no longer run your stage. So this integrated subsystem also provides that pressurization to the entire stage. So by eliminating batteries, hydrazine, and helium, we've removed the three life-limiting items for the stage. So ACES with an integrated subsystem can do the months or years on orbit. An interesting note is that the picture on the left, part of one of the items of this subsystem is actually an internal combustion engine. This is a 6-cylinder engine that we're putting on the back of the rocket. So that's how we're generating both the power and propulsion for the stage. So where do we go from here? Why do we want to use ACES? How do we expand what we're doing? As I mentioned briefly, there's definitely water on the moon. Some of the prior missions, specifically LCROSS, showed us that estimates run about 10 billion tons of water at each of the poles. There is a big research question about how do we get to it. And I know there's a lot of universities and organizations that are working on the extraction methods, but we know it's there and we know that it's usable. So once you extract it, how do you extract it potentially, and how do you actually get to it? So one of the concepts is that most of the ice is in a permanently shadowed region. So it means you don't have sunlight, you're not going to be able to run on solar power, so you need an alternative. One of the concepts is that you can beam power from the crater rims. Some of the crater rims do receive about 90% sunlight, so it's viable to collect the sunlight and then beam it into the crater. Other items that will need to be considered is extracting the ice, sublimating the ice, and then actually cracking or electrolyzing the water into liquid hydrogen and liquid oxygen. So wrapping up, ACES and Vulcan ACES is very much an enabler for the cislunar economy and for the commercialization of space. It is an entire transportation system that can be used for science, exploration, national security, and really anything else that we may want to do up there. So with that, I will wrap up and take any questions. Thank you.
I can't imagine what we can do with ice on the moon.
Me too.
So please, just two quick questions. When are you going to make a choice, the decision on the booster? Is that coming up pretty soon? And secondly, has your ACES been properly funded yet, or is it still going forward on a quarterly basis?
Sure. We have not made a decision on the first stage engines at this point. And for the second item, ACES is very much in development now. It's going very well. Yes?
Did I hear you correctly that you have 100% mission success, but that's based upon a Russian rocket that you're no longer using?
Let me clarify. So yes, sure. We do have 100% mission success under United Launch Alliance. That's correct. One of the rockets does have a Russian engine. It's an American rocket. Only the engine happens to be Russian.
Okay, so then does that 100% mission success rate give you better rates with the insurance people?
Yes, it does. Yes.
There's an abundance of H3 on the moon, helium-3. Have you explored the pros and cons of using that? And what did you discover?
I would probably say not in depth. Since we're building off of an existing second stage and its technology, there's probably more room for exploration of the helium-3 and how that might play into it. Yes?
So, I mean, like, once, you get these up there, I mean, how might that help enable, like, exploration of the, I mean, would it serve as a kind of staging ground, or is that just are those of extracting water and the idea of putting cases down? I mean, like, would you hope that ACES could deploy, say, drones on the moon, or is that just not?
Yep. So if I have the question right, it's really transportation between points, anywhere between Earth's surface to the moon's orbit, and anywhere in between, also including some near Earth objects, particularly L1. I'm not sure I'm addressing your question, though, so maybe I can follow up with you. That'd be great. Yes?
So it sounds like your reusability play is around the second stage. Do you have a view on landable rockets in order to meet SpaceX are doing?
Sure. So for the booster, it's to recapture the engines. We do not envision bringing the whole first stage back. For us, the engines are the most valuable part, so those are the part that we will recover from the first stage. Yeah.
Can you speak to the cycle of the engine? I presume it's the new engines on the ACES, not the RFMs. Can you speak to the cycle of them and how many restarts you're designing for?
Kind of. So I will say that we recently announced for the second stage, we have chosen Aerojet Rocketdyne to provide those engines. And I will say, as far as the number of restarts, that is probably a proprietary question. So that's not something that I can address here.
So thank you very much.
All right, thank you.